future.nottinghamuniversitystudent.com. Okay? Thank you very much.
Thank you, Alfredo, and thank you for inviting us and for inviting me and to all the organisers. Those of you who are from Pamplona, I was here about 3 months ago. I think I certainly talked to some of you. If I repeat myself, I apologise. I'll try to make sure that there's not too much there. A very different topic for this next session. We're moving away from the actual person who's eating the food and going to spend a little bit of time looking at the food itself, and particularly looking at those foods which are derived from animals, and I'm going to focus specifically on those foods which are derived from ruminant animals. That is red meat, beef, lamb, perhaps even goat meat, and dairy products, which are the milk from those animals, obviously in most parts of the world, predominantly cow's milk, but obviously other ruminant milk is eaten in some parts of the world as well. Just to remind you where I'm from the University of Nottingham. This isn't the main university campus, this isn't University Park, which is in the city centre. I'm based in the School of Biosciences, which is about involved in this sort of work. I'm a human nutritionist or a human nutritional biochemist by training, but when I moved to the School of Biosciences, there were a lot of people who were interested in agriculture, a lot of people interested in animal production, and I've had the privilege to collaborate over the last 20 years with many of them in looking at what we might do about some of the problems. Yes, people should change what they eat. People should eat less saturated fat, for example, but we've been telling them that for the last 30, 40, 50 years, and they don't tend to listen to us. Can we do it from another point of view? Can we actually change the nature of the food they're eating? Perhaps without them realising too much, so that we're doing them good if they can't do it for themselves. I like to start with some good news sometimes rather than all bad news, and the good news is that in terms of heart disease, we really have seen quite a dramatic change over the past 40 or 50 years. The slide here in blue shows the incidence of coronary heart disease in 1970 in various countries around the world. And then in red we have the incidence in the same countries in the year 2000. I was devastated to see when I was checking my slides last night before I went to bed that Spain isn't on the axis there. That's an omission that I will have to put right. Lots of countries but not Spain there, so I apologise for that. If you look in the blue, you'll see that the UK is over here. So I've standardised everything, obviously, to us. And you'll see that the countries above us, basically, were all those countries that we have managed to colonise, populate, and dictate what they eat, and they were all doing worse than us. So the countries that were doing worse than us in those days were Australia, Canada, we have New Zealand, and we have the USA. So all of those very westernised countries, if you like, all of them with an Anglo-Saxon bias towards them, were all by far the worst in the world. And then over the last 30 or 40 years, we've seen a dramatic decrease in many countries, in most countries, with the UK coming down to here, and all of those countries that we had exported our heart disease to actually doing better than us, so Australia, Canada, and the USA all actually having slightly lower levels of heart disease than we do. But it's not universal. There are some countries around the world where heart disease has actually got worse over that time. Many in Eastern Europe, so for example you've got Bulgaria there, you've got Hungary there. Mauritius is one of the worst, and I won't go into the reasons why that is with their particular problems with obesity and what have you. But overall, there has been a general decline in most of the developed world, at least, in terms of heart disease. Now, why is that? Well, as a nutritionist, I'd like to say that it was all due to us, and that we had told people to, as I say, what they should be eating, and they'd listened to us, and we had managed to have an influence, but predominantly that isn't the case. About 42% of the decrease in deaths from heart disease are due to improved treatment. So if you have a heart attack, then your likelihood of surviving that heart attack now is considerably greater than it was 20 or 30 years ago. The other, almost 60%, is due to an improvement in risk factors for developing the disease in the first place. And one stands out dramatically from all the others, and certainly in the UK and in many of the parts of the Western world, that decrease in heart disease, a lot of it is simply due to the fact that we have got one public health message over to a significant proportion of the population, and that is to stop smoking. And about 48%, almost half of the decrease in the UK that we've seen over the past 50 years or so, can be specifically put down to the fact that we have a reduction in the smoking of tobacco. There's also a small decrease in blood pressure. There is a decrease in our plasma cholesterol, thank goodness, but it's only about, accounts for about 10% of the decrease in heart disease. Social deprivation has gone down a little bit. But then, as we've been hearing a little bit already this morning, there are some factors which have actually got worse over the past 40 or 50 years, all related to obesity. We've got a reduction in physical activity, so that's a minus number when we look at the number of deaths postponed. We have an increase in obesity itself, and associated with that increase in obesity, of course, we have an increase in type 2 diabetes. Now, whether these factors, as they're getting progressively worse, are going to start to see us actually see that decrease in heart disease change again over the last 10 years, or at least slow down, we're not sure. But certainly, it's a little bit concerning that a whole raft of other risk factors associated with obesity are now taking over from the traditional risk factors for heart disease. But we're talking about nutrition, and I've used this slide on many times. If anybody else has seen it in the past, I apologize now. But it's interesting, I think, to note that historically, animal fat was associated with wealth, it was associated with a good lifestyle, it was associated with health, it was a good energy-giving part of our diet, and in the days when we did lots of exercise, it was felt that it was a good way to get the energy that we needed to do that exercise. Little did we know, back certainly in the post-war years, for example, little did we know that we were saving up a real problem for ourselves in terms of its impact on our plasma cholesterol and therefore our health. And then this guy had to come along and ruin it all. This is Ansel Keys. Probably most people will see him as the grandfather, if not now the great-grandfather, of the diet-heart hypothesis, the idea that consuming diets which are rich in saturated fat increases your plasma cholesterol, and by increasing your plasma cholesterol, you increase your risk of developing heart disease. He was responsible for two main bits of evidence back in the 1960s to suggest this. One was the so-called 7 countries study, the epidemiological study that is still debated about very violently as to whether it was a good study or not and whether he manipulated the data or not. But basically, he looked at 7 countries around the world and different populations within those countries and saw that their plasma cholesterols, the population plasma cholesterol, correlated very well with the population intake of saturated fat, and indeed that intake of saturated fat correlated very well with the incidence of heart disease, suggesting that the reason why some countries were seeing high levels of heart disease was that people were eating diets rich in saturated fat, increasing their cholesterol and dying of heart disease. Alongside that, and perhaps even more persuasive in many ways, he did a series of metabolic ward studies where he took people into the metabolic ward and fed them diets of defined composition and looked at what happened to their plasma cholesterol. And in response to that, what he saw was, again, a diet which was rich in saturated fat increased their cholesterol, a diet which was rich in polyunsaturated fat decreased their cholesterol, and we got what many of us know as the Keys equation, which was an equation which would predict the change in their total plasma cholesterol in response to changes in diet. And I think most people will accept that that has stood the test of time very well. And hundreds, if not thousands, of subsequent studies have been done, more or less showing that what Keys showed was right. The one thing that I should point out at the end there is there's also a factor of dietary cholesterol, and in fact, dietary cholesterol isn't probably particularly important, certainly for the vast majority of people, unless you've got really excessive intakes, because the change in your plasma cholesterol is associated with the square root of your intake. So for every milligram you take in, your plasma cholesterol is likely to increase by a function of the square root of that 1 milligram, which isn't very much. There may be people who are more sensitive. There may be people on very, very strange diets where they're eating more than maybe 3 or 4 eggs a day where it'll have an effect, but in general, probably isn't that important. What Keys couldn't tell us, because he didn't actually separate the individual lipoproteins in the plasma of his subjects, was what the effect was on the actual lipoproteins. And of course we have our bad cholesterol, as the population knows it, low density lipoprotein cholesterol. We have our good cholesterol, our HDL, which actually protects us from heart disease. And what is the impact of these different sorts of fats on these? And a whole range of studies have been done in the intervening period to actually look at this effect, and periodically there will be a meta-analysis of some sort done, bringing the best of those studies together to see what the effect was. And one of these was the one by Ronald Mensink in 2003, where he looked at the effect of these individual fats, not only on total cholesterol, but on the lipoprotein fractions. Something's happened, my colours have changed. That is saturated fat. What's showing up as a blue bar there. But basically what it's showing is that yes, saturated fat increases LDL, but it also increases a little bit the HDL, which offsets some of the bad effects. But the increase in LDL is greater than the increase in HDL, therefore overall saturated fat is bad for you. Monounsaturated fats, which Keys tended to ignore because he thought they were neutral, and that was because there is a small decrease in LDL, which is almost balanced out by a small increase in HDL. So when you look at total cholesterol, there's not a lot going on, but there is some benefit of consuming monounsaturated fat on your lipoprotein cholesterol levels. And then you move on to the polyunsaturated fats. Primarily here we talk about N6 or omega-6 polyunsaturated fats, predominantly linoleic acid, and you can see an even bigger decrease in LDL, also a modest increase in HDL, so polyunsaturated fats are good for you. And what Keys told us all that time ago was that saturated fats were probably about twice as potent at increasing cholesterol as polyunsaturated fats are at decreasing it, and that seems to be borne out by the modern data, with LDL going up about twice as much with the saturates as it comes down with the polyunsaturates. The other type of fat which was added to the equation here, which Keys didn't look at, was the trans fatty acids. Those fatty acids which contained a trans double bond, and these were shown to be the type of fat which were most potent in having an adverse effect on our lipoprotein cholesterol, increasing LDL cholesterol the most, and if anything having a very slight HDL cholesterol lowering effect. So there's no offsetting of this effect by a good effect on HDL like there is in the saturates. And this confirmed that trans fatty acids were the worst, if you like, in our diet. And data like this has been behind the move across much of the developed world now to actually try and minimize the amount of trans fat in our diet, predominantly by reducing the amount of hydrogenated fat which we use. We'll talk about in a moment. Until recently, most of that trans fat came from hydrogenated vegetable oil in margarines and shortenings, in our cheaper cakes and pastries and things like that. In many countries now, there's been a concerted effort to reduce or almost eliminate the use of such hydrogenated fat, and that's changed the sources of trans fat in our diet quite substantially. So most countries have dietary recommendations originating back to that work by Ansel Keys, suggesting the levels that the population should be taking in. Rather than put the UK ones up, I've put the World Health Organization ones up here, very, very similar to ours and very similar to those in most of Europe and indeed North America, Australasia, and so on. Suggesting that our total fat should not really exceed 35% of our energy intake. Saturated fat should be about less than about 10%. Monounsaturated between about 15 and 20. Total PUFA between about 6 and 11, being made up of 2.5 to 9% N6 PUFA, 0.5 to 2% N3 PUFA, and that trans fat should be less than 1%. Each country might have slightly different versions of that, slightly different values, but they're more or less all based on that. We have, certainly in the UK and in many other countries, we have changed what we eat, apparently. This just shows the consumption of some animal products in Great Britain, and you can see that from the mid-1970s until the mid-2000s, there was a drop in the consumption of beef, which seemed to stabilise about 1995. Now, we've got all sorts of problems with beef in England. We've had so-called mad cow disease, BSE. We've had foot and mouth disease. We've had all sorts of factors which have influenced beef intake. But hopefully some of the health messages about heart disease have got through as well. Lamb, meat from sheep, has also gone down again, but it has stabilised over the last 10, 15 years or so. And the consumption of butter has gone down, been replaced by low-fat spreads. And again, that seemed to stabilise around 1990. So we did seem to listen to some of these messages early on, but then we seem to get complacent again. We've changed dramatically what we drink in terms of milk. The consumption of whole fat milk has gone down quite dramatically and continues to, and has been replaced by reduced fat milk, skim milk or semi-skim milk, replacing it as our drinking milk. Unfortunately, our consumption of things like cheese, yogurt, cream, all of those things has tended to gone up and have negated that effect to a certain extent. So in the end, the total effect on saturated fat intake has not changed quite very dramatically. Went down initially, we got to the mid-90s, and we have stubbornly refused to go any lower. We're not getting down to our level of 10% that we're trying to get down to try and minimise our risk of heart disease. And in the face of this failure to get the population to change their intake further, do we need to change the food that's available to them? And that's what I want to spend the rest of my time talking about. Where are these bad fats coming from? Well, in 2009, in the UK, the suggestion was about 22%, probably can't see that from the back, I'm sorry, about 22% of the saturated fat was coming from milk and milk products. Another 26% was coming from meat and meat products, about 4% from butter. So we've still between 50 and 60% of our saturated fat was coming from animal products. On the other hand, in terms of the trans fatty acids, the picture looks very, very similar. About 22% of our trans fatty acids in 2009 were coming from milk and milk products. Another 25% from meat and meat products, and again another 4% from butter. Almost exactly the same as the saturated fatty acid. And this highlights one of the consequences of us taking out the trans fat from our diet by reducing the amount of hydrogenated vegetable oil that we're putting into our food chain. Because no longer are margarines, no longer are shortenings the major source of trans fatty acids. Animal fats, specifically those from ruminants, are now the major source of trans fat in our diet. And I'll come to at the end of my talk, there's still a massive debate about whether that's a good thing or a bad thing. Are those trans fatty acids that we find in animal products bad for us like we know the hydrogenated fat was, or actually are they associated with some potential health benefits? So over the years I've been involved in various projects, and I'll say right up front, not particularly successful projects, because these are very stubborn creatures to work on, to try and manipulate the composition of meat and milk, specifically from ruminant animals. In a non-ruminant, in a pig for example, it's relatively easy. A pig's fatty acid will actually reflect what you feed it. If you want to feed it sunflower oil, then the pig tissues will become enriched in linoleic acid. If you want to feed it olive oil, they'll become enriched in oleic acid. The ruminant, for reasons which I'll go into in a moment, is very, very different. The reason we don't tend to do it is because it's expensive to feed pigs olive oil, obviously, or sunflower oil or whatever. So it hasn't really been taken up. But these animals pose particular problems. Two main problems. First of all, they have this thing called the rumen, which is full of bacteria and other microbes which change the nature of whatever you feed them. So you might feed them a diet which is rich in unsaturated fat, but what comes out of the other end and gets into the animals is very different, as we'll see. Secondly, they do not eat high-fat diets. Their diet is inherently low in fat, and if you increase the fat content of a ruminant's diet too much, you will stop rumen function, you will make the animal ill, and it will die. So you can't increase their fat consumption too much to try and change it. So a lot of the fat which accumulates in the body, in their muscle tissue, in their fat tissue, in their milk, is actually made by the animal themselves. So in the background there you have the stomach of a ruminant with its various compartments, and basically what we find is that if a cow is eating grass or eating cereal like they often fed in some parts of the world, including the United States, they're taking in high levels of linolenic acid, 18 carbons, 3 double bonds, and high levels of linoleic acid. But once it gets into the rumen, the bacteria and the other microbes that are living there actually start to metabolize those fatty acids, partly because polyunsaturated fatty acids are actually toxic to those bacteria, and through a series of intermediates, which include some which contain trans double bonds, including conjugated linoleic acid, which we'll say more about later, producing relatively large amounts of this particular trans fatty acid, vasenic acid, trans 11-18-1, but converting vast majority of it into a saturated fatty acid, stearic acid. Now that might not be too bad in itself, because stearic acid is an unusual saturated fatty acid in that it probably doesn't raise our cholesterol the way some of the others do. So palmitic acid with 16 carbons, myristic acid with 14 carbons are very potent at increasing plasma cholesterol. Stearic acid is fairly neutral, but it is a saturated fat. It certainly gives ruminant meat the appearance of being very saturated. If you leave beef or particularly lamb to go cold, it goes very waxy. That's the stearic acid content of it. And you're losing your good fatty acids because they're being converted to this neutral fatty acid. And you can demonstrate that very well. This is some of our own data, simply by feeding an animal, measuring the fatty acid composition of the feed, and then literally drilling a hole through into its stomach and sampling the contents of the so-called abomasum after it's been through the rumen, and you'll see there's some big changes. These are some of our sheep that we've fed on preserved grass in the form of grass nuts. Grass is very, very rich in linolenic acid, relatively rich in linoleic acid, small amount of oleic acid, some palmitic acid. By the time it's got through the rumen, through the stomach of the animal, by the time the bacteria have had a go of it, you see you've lost virtually all of your good fat. You've lost all of your linolenic acid, you've lost all of your linoleic acid. Most of it has been converted into stearic acid. The only thing you don't lose is the bad fat, the palmitic acid, unfortunately. So simply feeding a ruminant on a diet, changing the nature of the fat in their diet, does not necessarily change the nature of the fats in their tissues or indeed their milk. In terms of the fat they synthesize, then obviously that is synthesized from, tends to be synthesized from volatile fatty acids, rather than from glucose in a ruminant, because a ruminant diet is inherently low in glucose. Basically, same sort of pathway going through fatty acid synthase. The main products are palmitic acid in the adipose tissue. That can be elongated to produce more stearic acid, and we can, and we'll talk about this more later, then add one double bond to make oleic acid through the action of the enzyme stearoyl-CoA desaturates. Slightly different in their mammary gland, in that during the fatty acid synthase reaction, which is going on here, it's much more leaky. This one tends to take all of malonyl-CoA all the way through to palmitic acid. In the mammary gland, you leak these shorter chain saturated fat. So there's a lot of C12, C10, C8, C6, a lot of shorter chain saturated fatty acids appearing in milk. And this may be a physiological adaptation to benefit the offspring. They tend to be absorbed a lot faster, can get straight into the bloodstream, and can provide a source of energy for the offspring. So that may be the reason for that. They also seem to apparently lack the elongase in the mammary gland, so they can't convert C16 naught into C18 naught. Of course, this can come from the diet, or it can be released from the adipose tissue, so you can get this, then you do that. But actually, elongating palmitic acid isn't an option in the mammary gland. So those are the two things that are going on. You've got fatty acids coming in from the diet, but they're being modified substantially by the rumen. You've got the animal making fatty acids, predominantly making saturated fatty acids, but with the one option potentially of converting some of those saturated fatty acids into oleic acid through the action of SCD. And the bottom line is this. This is a typical composition of cow's meat, beef, and cow's milk. The milk, as I say, tends to be enriched in these shorter saturated fatty acids. Both are very rich in palmitic acid, one of the bad guys in terms of increasing cholesterol. Relatively high levels of stearic acid. Surprisingly, perhaps after everything I've said, very high levels of oleic acid. So the animal is actually converting quite large amounts of its fatty acid into oleic acid through the action of that enzyme SCD. We've often wondered why a cow or a sheep would bother to take saturated fats and convert them into a monounsaturated fat. And the best reason I've had suggested is purely it helps the cow to keep fluid. It stops it becoming solid. If you imagine a mountain goat in the middle of winter when it's minus 30 outside, if all of its fat was palmitic acid, then I suspect the potential actually could be that it actually almost solidify at those temperatures. But if it's converting a significant amount of that to oleic acid, that may be one reason it may help. Then very small levels of unsaturated fatty acids, but then here we've got some trans fats, and we'll come back to that in a moment. So is it really bad? Is the fat composition of beef such that it will actually increase your cholesterol and increase your risk of heart disease? Well, certainly if you're one of these guys, it is. This is one of our animal models that we use of heart disease. This is the Apoe-Leiden mouse, provided for us by Louis Havikis. And as the name suggests, arising from a mutation which was discovered in Leiden, a mutation in the protein, apolipoprotein E3. And people who carry this particular mutation have a considerably increased risk of heart disease, have increased plasma lipids, and this mutation has now been put into the mouse, and sure enough, it gives the mouse the same properties. The mouse will develop hyperlipidemia on a high-fat, high cholesterol diet, and it will develop heart disease. So we've used this in a variety of studies. We feed our animals, in this case, a diet containing 36% freeze-dried beef, which seem to like a lot. And when we've supplemented that with a small amount of unsaturated fat in one group with rapeseed oil, and you'll see the effect of that in a moment. And after 12 weeks, we kill the animals. We take sections of the aorta just through here where it joins the heart. We get cross sections like this, and we can then stain them for lipid, for the accumulation of lipid within the artery wall with oil red O, and we can quantify that, and it gives us a level of atherosclerosis. So we fed one group of mice on a diet which just contained this 36% beef as the only source of fat in its diet. As you can see, compared to the recommendations, they're not too high in total fat at all, but relatively enriched in saturated fat, and particularly low in unsaturated fat. MUFA is low, PUFA is very low. And then we compared that to a group where all we did was add an extra 4 or 5% of rapeseed oil. So we've increased the total fat a little bit, but in doing that, we've reduced the total proportion of saturated fat, though the absolute amount obviously stays the same, but increased the proportion of monounsaturated fat and increased the proportion of polyunsaturated fat. Our animals are very hypercholesterolemic on our beef diet. They have a plasma cholesterol of about 10, which in a human would be considerably high. Because of the particular nature of the type of hyperlipidemia they develop, they tend to accumulate lots of what we call remnants within the chylomicron VLDL cholesterol range, but their LDL cholesterol is relatively high, about 2, compared to their HDL, which is low. And a so-called non-HDL to HDL ratio, which perhaps is a ratio of their risk, is particularly high, around about 8. Simply by putting that little bit of unsaturated fat in their diet, we can change that quite dramatically. Their total cholesterol goes down, their chylomicrons and VLDL goes down, their LDL goes down quite dramatically. Their ratio is halved. And in doing that, first of all, our animals fed the high-fat beef, we can see develop quite substantial lesions. All of this red along here is an atherosclerotic lesion developing within the aorta of the animal. If we fed them for longer, that would get bigger. We've never seen 1 kilo over a heart attack, but they certainly they start to narrow the artery. Simply by replacing it with a little bit of unsaturated fat, we almost completely eliminated the presence of those lesions. And if you look along the length of the aorta, here are animals who are fed on the beef alone, lots of atherosclerosis right along the length of the aorta. So this is going from the heart in this direction towards the aortic arch in that direction. And as you can see, we've virtually eliminated all of that atherosclerosis when we put that bit of unsaturated fat. So what that told us was it was worth pursuing. If you can get the beef to change its composition, not particularly dramatically, by a relatively small amount, its potential impact on heart disease could be quite dramatic. Obviously, people don't just eat beef like our mice did, but you could actually then sell that meat as a functional food almost, a food which has been enriched in unsaturated fat, which will counteract the effects of the saturated fat. So one of the things that we've looked at over the years is this enzyme, because this enzyme, stearoyl-CoA desaturase, has the potential to reduce the amount of saturated fat and increase the amount of monounsaturated fat. So is there anything we can do to get this enzyme to be more efficient in our ruminant animals? It certainly seems to be important in regulating the composition of the tissues. This is a study we did in growing lambs, where we took a number of lambs, I can't remember, quite a large number of lambs, slaughtered them at different ages as they were growing before they became ruminant, and we looked at the amount of message for the SCD enzyme as a measure of its activity, hopefully, or a proxy of its activity, and we looked at the amount of oleic acid in the tissue. And sure enough, those animals who had the highest level of SCD mRNA had the highest level of oleic acid, and vice versa, a very nice strong correlation. So it does seem important in governing the amount of oleic acid. Equally, if we take animals of slaughter weight, if you like, and this was done in sheep as well, and we look at a whole range of different adipose tissue depots, we find they have quite different amounts of oleic acid. And this time it's expressed as the amount of oleic acid divided by the amount of stearic acid, product-precursor relationship. So this depot in the sternum had relatively high level of unsaturated fat. Perirenal, within the animal, around the kidneys, had a very low level of unsaturated fat and was more saturated. And again, if we looked at the expression of SCD, we found that that went down in exactly the same proportion. So again, SCD seems to be very important in governing the composition of those tissues. So what could we do to actually increase this enzyme and improve the fatty acid composition of either meat or indeed milk? Ideally, if we could change the diet of the animals, that would be great. If we had to give them something, it becomes more problematic in terms of hormones or growth promoters or whatever, in terms of consumer acceptance. Are there genetic differences in the expression of this enzyme that we can actually exploit in conventional breeding terms and actually produce animals which have got more SCD, therefore produce more unsaturated fat? The one thing we'd love to do, and we've tried to get funding and nobody will fund us at the moment, is to actually overexpress this animal in a ruminant, this enzyme in a ruminant, and prove that if you get increased expression of the enzyme, you can change the tissues. Obviously, in most of Europe at the moment, the idea of using genetic manipulation in farm animal production is one that the public aren't willing to accept and funding bodies aren't willing to fund, unfortunately, at the moment. It can be done in a test tube, and it can be done relatively simply. Basically, insulin has a major effect on the activity of this enzyme, and if we take little pieces of adipose tissue and keep them in a test tube, treat them with different hormones, we can get quite big differences in the type of fat they're producing. So we've got control, we've got insulin, we've got a glucocorticoid, a synthetic one, dexamethasone, or we've got them both together. Here we look at the amount of mRNA for SCD, and you can see the insulin SCD mRNA, with insulin it goes up quite dramatically. Glucocorticoids tend to put it down. In the presence of both, insulin seems to prevail. But more importantly, the type of fat that these explants are making, as we call them, these little bits of adipose tissue, changes quite dramatically. So as SCD goes up here, the proportion of unsaturated fat that this fat is making is dramatically increased. Vice versa, when you put the glucocorticoids in, proportion, virtually no monounsaturated fats made. So it's simple. If we could increase the insulin concentrations in the animal, we'd increase the amount of monounsaturated fat that you can produce. In practice, that's very, very hard. To change the amount of insulin that a ruminant animal is actually producing is very, very difficult because you can't really manipulate its diet to any great extent. As I say, anything you do to the diet can impact on ruminant function. Yeah?
I just start by asking questions because I think other people should do.
Yeah.
Just to start the discussion. Isn't this actually, you're saying that adding insulin is a good thing.
Yeah.
But how about just improving insulin sensitivity? Because, what you saw here that in dexamethasone, but you probably you induce insulin resistance. And so, can you just comment on this? Would this work not by adding insulin to animals, but just by improving insulin sensitivity, which obviously is beneficial?
There's absolutely no reason to believe that it wouldn't. How you would do it, again, is difficult. But it's interesting because, ruminants do go through periods of insulin sensitivity. For example, in lactating cows sometimes go through quite severe periods of insulin resistance and what have you, and that may be having an impact in itself. But that obviously that would be a more appropriate way of doing it if you could. You're not going to get big leaps in insulin. If you look at the insulin profile of a ruminant, it's very, very flat across a day. They don't have the spikes of insulin because they don't tend to have the spikes of intake. Yes, so one of the more likely things would be insulin sensitivity. I should have said, if anybody else wants to ask a question, please feel free. I'm more than happy to stop talking and try and answer. So that's a proof of principle, if you like. It proves that this enzyme, if you do manipulate it, it does change the composition of the fat. But I'll be perfectly honest with you, we haven't found any way of doing it systematically in a live animal. In terms of genetics, we've also shown that there is some possible way forward. In this one, we've gone into dairy cows here, and we've actually taken the cells which actually come off in the milk. Whenever you milk a cow, there are some cells in there. You can isolate those cells, and you can actually measure mRNA in those cells, and that's basically what we did. You measure the fat content of your milk, and what we found was if the higher the level of SCD mRNA in those cells which come off in the milk, the higher the ratio of 14:1 to 14:0. Now this is a good measure of the activity of that enzyme. So there were some cows with higher levels of SCD, and they did seem to produce more unsaturated fat. And one of my colleagues, Phil Garnsworthy, who's an animal productionist, in a large group of 2,000 cows, has suggested the heritability of desaturase is something like 0.3, which is quite high and probably means you could go into your national herds of cows and you could select for those animals which were producing high levels of SCD, and you could potentially increase the monounsaturated fat content of your milk by that method. Okay, to move on, what can we do through diet? The figure here just shows the fatty acid composition of beef from 3 sets of cows. One set of cows which were fed grass, which perhaps is what you think they should be fed on. One was fed concentrate specifically, which tends to be barley and straw and things like that, which is often used in what we call feedlot cattle. The United States are probably the biggest at doing this, keeping their animals in enclosed spaces and feeding them large amounts of cereal crop. And then the third one was just some beef that we got from a local butcher just for comparison. And you can see that in terms of the gross fatty acid composition, there are some changes. I don't know what our local butcher was doing, but in fact he was selling beef which was lower in saturated fat than either of our two groups. There's some differences there. As you can see, the concentrate produced less stearic acid compared to the other two groups. Very similar in the amount of oleic acid. But one of the big differences is when you get to these minor fatty acids, the unsaturated fatty acids, polyunsaturated fatty acids, if you feed concentrate, you tend to have low levels of linolenic acid and high levels of linoleic acid. If you feed forage, then the amount of linoleic acid is somewhat higher than the amount of, sorry, where are we? Yeah, that's it, of linoleic acid. So there are some minor differences, but nothing particularly great. We can manipulate that. You can feed the animals some specific oils, and here's an example of feeding either linseed oil or fish oil. And as you can see, when you feed linseed oil, you do get a little bit more linolenic acid accumulating. When you feed fish oil, you do get a little bit of EPA and indeed DHA accumulating, so you can do it, but it's always muffled by the fact, it's always suppressed by the fact that a large proportion of those fats are actually being saturated within the rumen. The alternative to that is to protect that lipid in some way, and you can actually coat the lipid in protein so it's not broken down in the rumen. And if you do that, you can get a lot of unsaturated fat through. For example, this is a mixture of different polyunsaturated fats, and you can see you get a lot of linoleic acid particularly through into the tissues of the animal if you protect it. That technology has been around for quite a long time. The problem is making it workable in a commercial setting, because it's expensive to do this. It changes the way that you actually feed your animals, and as a result of that, it's never been taken on yet commercially. If it ever is, I suspect it will be done in dairy cattle, because there is a premium on your dairy products and changing the fatty acid composition of your dairy products. Dairy products are seen often as functional foods. We see plenty of examples of them within the market. So I suspect that we may see eventually a protected lipid being used in this sense. Finally, just to move on to say a little bit about milk itself. We've talked about the fatty acid composition of milk, and remember it differs from beef and meat because it's got these shorter chain saturates in. Still has quite a lot of oleic acid in. It's very low in polyunsaturated fatty acids, but it does have this trans fatty acid here, and it has this fatty acid called conjugated linoleic acid. I'm sure you've all heard, I hope you've all heard of conjugated linoleic acid. There's been a vast amount of interest in it over the last 20 years or so. if you go back 10 years, it was seen as the solution to all of our problems for every single disease you could actually think of. Every week there'll be another paper saying it protected you from something or other. Conjugated linoleic acid contains multiple double bonds, or 2 double bonds, but unlike normal linoleic acid, there isn't a methyl group between the 2 double bonds, and one of those double bonds is in a cis conformation, and the other one is a trans conformation. Ruminant meat and ruminant milk are the only natural sources of CLA. They're a result of the action of the microbes in the rumen, but we can make them by chemically from vegetable oils, and there are various preparations out there in your health food shops which are mixtures of different isomers of CLA. The one which occurs predominantly in meat and milk is this one, cis-9 trans 11. And there is a reasonable amount of animal evidence that it may have some anti-carcinogenic effects. There's also some animal evidence, as I'll show you in a moment, that it may have some anti-atherogenic effects. So people within the milk industry jumped on this quite quickly, saying, at last, some good news about milk. We can tell everybody it's the only natural source of CLA, and we can sell it on that basis. I should say that the biggest effect of CLA which has ever been reported is this one, altering nutrient partitioning and reducing the amount of fat. And if you take chemically produced CLA and you feed it to a mouse, within a few weeks it virtually loses all of its adipose tissue, all of its fat. And that caused obviously a great deal of excitement. There's 2 problems. First of all, it was found that the active isomer within that wasn't our natural one, our cis-9 trans 11. It was trans 10 cis 12, which is only found in any quantity in artificially produced CLA. But perhaps more importantly, when you give it to humans, it does virtually nothing. So if you've got a fat mouse and you want to get it thin, great, give them CLA. If you've got a fat human, it's probably not the answer, unfortunately. But these other things, the anti-carcinogenic effect and possibly the anti-atherogenic effect, might be more worthwhile. CLA gets into these animals in 2 ways. Some of it is directly produced in the rumen through these pathways that I showed you. However, the largest proportion is actually made from this, which is also produced in the rumen, trans 11-18-1, gets into the animal. Along comes our enzyme again, the one that we've been working on for 20 odd years, stearoyl-CoA desaturase. It adds a double bond in the 9 position and converts our trans fatty acid into CLA. And this is where the argument has come about whether this is bad or good. Is trans 11 bad because it's a trans fatty acid, going to put our cholesterol up, or is it good because it's a substrate to make CLA from, which might be good for us? We can change the composition of milk by altering the diet of the cow to a certain extent, and this was a study that we did in collaboration with our colleagues in Cornell, with Dale Bauman. And basically he added a bit of sunflower oil, a little bit of fish oil, and that changed the production of CLA, and he produced the cows which are producing the highest level. And as you can see here, he's quite dramatically increased the amount of CLA. It's still not high, but it's considerably increased compared to before. We'll come back to this in a moment because he also increased dramatically even more the amount of trans 11 C18-1. We fed this to hamsters, another animal model that we use of cholesterol metabolism, and we were very pleased with the results. The CLA, racemic acid enriched milk, reduced LDL, had a non-specific increase in HDL, it reduced the LDL-HDL ratio. So this milk, which was enriched in CLA, seemed to decrease the bad cholesterol, potentially protect the animal. And in a number of other studies in animal models, there seemed to be some benefit of CLA increase. But perhaps the most intriguing thing was that this milk was increased with CLA, but it was more increased in this trans 18-1. Is that good or is it bad? We know that trans fats we're told trans fats are bad. They've been banned in many countries, or specific efforts to try and reduce them to a minimum, primarily, as I say, however, through reducing hydrogenated vegetable oil. The trans fatty acid we find in our milk is very different to that we find in hydrogenated vegetable oil, in that it is nearly all this trans 11, while hydrogenated vegetable oil has this wide range of different isomers. So because we can convert that trans 11 into CLA, does that make it actually different from the trans which we find in hydrogenated vegetable oil? So unlike other trans fatty acids, succinic acid does not increase plasma cholesterol, as a significant proportion is converted to cis9 trans 11 CLA. That's our hypothesis. We tried to test it again in our hamsters by creating different diets. We had a control diet, a diet rich in hydrogenated vegetable oil, a diet rich in elaidic acid, trans 9 18-1, a major component of that, and a diet specifically enriched in vicenic acid, trans 11. And we fed this to our hamsters and we looked at the effect on their plasma cholesterol. And the result we got was not what we expected. Compared to our hydrogenated vegetable oil, vicenic acid did put VLDL cholesterol, LDL cholesterol down, but the elaidic acid, the trans 9, also put it down. So both of the pure trans isomers seem to put cholesterol down, not just the vicenic acid. And we failed to be able to explain why that's the case. So overall, partially hydrogenated vegetable oil is bad for you. It's a total cholesterol to HDL ratio. The non-HDL to HDL ratio both go up. That's bad for you. But our pure isomers, if anything, both of them are good for you, suggesting that neither trans 9 nor trans 11 are responsible for the bad effects of this. So our hypothesis remains to be proven or otherwise. And then from the group of Martin Catan, this meta-analysis came out which suggested that all trans fatty acids are bad for you, that you can put them all on the same graph in terms of increasing LDL cholesterol, whether it's industrial trans, hydrogenated vegetable oil, the open circles, ruminant trans, essentially vicenic acid, the diamonds, or indeed CLA, the circles. He claims that they all fall on the same graph. I'm not a good mathematician, but it does worry me that all of these points are down here and all of these points are up here with the exception of these two. Because normally we consume much lower levels of animal trans than we used to, certainly, of hydrogenated trans. They argue that that is acceptable. Many people I know have expressed concern about the fact really we need some studies with high levels of animal trans to see whether that fits. Equally, he says, in lowering HDL, they all fit on the same line, but exactly the same thing fits. All the animal trans are all clustered towards the left-hand side. Okay, I realise it's been a long morning. Just some conclusions from me. Animal products, particularly ruminant meat and milk, continue to contribute significant amounts of saturated fat to the human diet. Over 50% of the saturated fat that we eat tends to come from a combination of meat and milk. As we have reduced other sources of trans fat in the diet, they have increasingly become the major source of trans fat in our diet. And we don't know whether that's good or bad, whether we should be worrying about it or not. There may be some scope for genetic selection to actually reduce the saturated fat content of these products. There are some dietary strategies you can use, but it does mean changing the way you feed your cow. That in itself may be expensive to the animal, to the farmer. And if you're going to use protected lipids at the moment, they are beyond the reach of being commercially possible. And there's still some uncertainty about the impact of animal trans fat on human health. Does CLA really have any benefit for us, at least the cis9 trans 11? Does vicenic acid have a neutral effect? Does it have a beneficial effect? Does it have a negative effect? Still really needs to be answered. That's what we really like to do, but as I say, getting the funding for that at the moment is going to be rather difficult. And just to finish with just acknowledging some of my collaborators, both in Nottingham and elsewhere, over the last 20 years or so of looking at this problem. Happy to answer any questions, though I'm sure you're all worn out and tired by now. Anybody? Yeah?
I have a question. I know that using bacteria in yogurt, they are able to produce plaque outside of the cow. But I guess that if they use probiotics maybe in the cow, changing the flora of the cow, would it be possible to increase the production?
That's an interesting question. I mean, first of all, the nature of the bacteria are very different. The bacteria which are living in the rumen are highly anaerobic. It's a non-oxygen environment. So what can actually survive in there is very different to what you could use in a culture. So I don't think you could take the same bacteria that you use in the fermentation process and use them. But your question is a very good one, and people are starting to look at it. Can we change the nature of the bacteria that are living in the rumen to change the sorts of fatty acids they're producing? To make them produce more CLA if we want to do that, make them produce less stearic acid if we want to do that. And so people are trying to look at it. The trouble is that there's literally thousands of different bacteria living in the rumen of a cow. And so there's lots of rumenomics, if you like, going on at the moment, trying to identify which bacteria are doing which. So I don't think you could use the same one as you use in yogurt, but the potential for manipulating that bacterial population is definitely there, yeah. Anything else? Okay, thank you.
Only I want to know if you drink milk.
If I drink milk? Yes, I do drink milk. I drink full-fat milk. And I'm ashamed to say I also eat butter. I stopped eating butter. I then found my cholesterol was elevated. I was put on statins. My cholesterol's gone down, and I've gone back to the luxury of eating it. But, I mean, not in excess, but I do drink it. And I mean, certainly in terms of milk and dairy products, there's many reasons for us not to want people to stop drinking them, I think. There are important nutrients in there. I mean, obviously you think of calcium, particularly as an important nutrient. It is a very important source of energy and what have you, particularly in young children. So it's the one food, particularly if we could manipulate it, if we could just improve that fat acid composition a bit better, I think it could have major benefits, I think.
Sorry. May I ask you a small question? A tricky one. You've talked that the protect lipids that you gave to the ruminants will make the industry to change all the way they work. Could you tell us, if it's possible, if you can imagine a baby state is worth €1, how much you would worth with these protected lipids?
I can't, but I can tell you that it's not economically viable at all at the moment. I mean, they're ridiculously expensive. And people have tried a variety of ways. I mean, if you feed whole grain rather than crushed grain, if you feed whole sunflower seeds then that protects it to a certain extent. But there's nothing yet really which has got to the level where it would be commercially viable. If it is ever going to happen, I'm pretty sure it will happen in the dairy industry rather than in the beef industry. Because we already see milk. We see milk which is enriched in omega-3, for example. So I can see that people will be willing to pay more for that. Getting people to go along and look at 2 steaks and think, oh, I'll pay twice as much for that one because it's got 10% more linoleic acid, I think will be a much bigger challenge. So I'm sure it's been worked out. I'm sure there's some agricultural economists have done it, but I've just been told that it's nowhere near being economically viable at the moment. Yeah.
All right, thank you. Are there any more questions?
What do you think maybe it's a bigger problem in the confectionery industry, I mean the production of waffles and such stuff, if we take children, for example, and if we take prevention and cardiovascular diseases and the time needed to develop
yeah. In terms specifically of direct effects on coronary heart disease, I would still say that as far as we're aware, the amount and the type of dietary fat seems to be the most important. However, I think what you say is absolutely right in many ways. Contentious to a certain, but many people believe that the combination of a high-fat, high-sugar diet is obviously what's leading to obesity, obviously potentially could be leading to insulin resistance. We then end up with metabolic syndrome, and that is another risk factor in itself for heart disease. So those emerging factors, those emerging risk factors are potentially the high level of refined sugar in our diet combined often with a high level of fat as well. I mean, in this country, I'm not in the wrong country, in the UK and many parts, until 10 years ago as well, hydrogenated fat was being used in the cheaper sorts of food, in the bought cakes and the pastries and the biscuits and for making potato crisps and chips and what have you. I know in some parts of Eastern Europe still, they're still using large amounts of hydrogenated fat. So if they've got that, they've got high saturated fat, high hydrogenated fat, and a high sugar diet, I can see why perhaps we're seeing that while a lot of the world has got a decrease in heart disease, in some parts of Eastern Europe it's going up. So specifically on heart disease, I think fat is most important, but I think the combination of a high fat, high sugar diet is obviously what's leading to obesity, and that in itself is a risk factor for heart disease.
So now we have the coffee break, it was supposed to run from 11 o'clock to 11:30, so now it's more or less almost 11:20. So I think we can come a bit later to 11:40, but try to be accurate with that.